In this next example, I've got two trig expressions that are actually kind of equivalently complicated. And I want to prove that they're equal to each other. So this is verifying an identity. Again, I've got these three different approaches. I could start from the left side and try to simplify and end up with the right side, or I could start on the right and try to end up with the left, or I could maybe work on each side and hopefully get to a third equivalent expression for each of them. I'm not sure exactly which one I should do, so I'm just going to start on the left side, and if I get stuck, then I'll work on the right side, and hopefully we'll come up with something as we go. All right, so as I look at this one, the cotangent I know is 1 over the tangent, but I also know that it's the cosine over the sine, right, using a quotient identity. I'm just kind of looking through this. I can't really use a Pythagorean identity because there's no squares involved. I can't use an odd-even identity. There's not a lot of algebra tricks that are obvious. I can't do any factoring or anything weird like that. So I'm just kind of stuck with either a reciprocal or quotient identity. I could turn everything in terms of the tangent. That's a possibility as well. Or I could maybe use sine and cosine. I'll just go with sine and cosine because we've been doing that a lot, and maybe that'll help us out here. So let's take the cotangent. I'm going to write that in terms of the sine and cosine. So that would be equal to the, keep this over to the side here, cosine of alpha. Now alpha, you'll see a lot of Greek letters as your angles. Like we've seen theta before, and you'll start seeing alphas and betas and other things in there. So this is an alpha, it's a Greek letter. So cotangent of alpha plus 1 becomes cosine over the sine of alpha plus 1. And that's divided by, the cotangent again is the cosine of alpha over the sine of alpha minus 1. Okay, so that's using a quotient identity. Using it twice, but that's fine. This is a complex fraction, right? It's got a fraction inside of a fraction. I think one of the best ways to solve or simplify complex fractions is to combine the terms on the top and the bottom. So I'm going to turn these 1's into a common denominator with the signs. So it'll be sine over sine and sine over sine. All right, so it's going to look a little bit complicated, but we'll work through it. So this is the cosine of alpha over the sine of alpha plus this 1, to get the common denominator, becomes sine of alpha over the sine of alpha. Right? 1 is sine over sine, or sine over sine is 1, whatever. That's all over this fraction, cosine alpha over sine alpha minus 1, and that 1 is going to be the sine of alpha over the sine of alpha again, so that we get common denominators here. So that's going to be, multiplying by, sine alpha over sine alpha, which is really just 1, right? So you're just multiplying 1 by itself, 1 times 1 to give you sine alpha. Something like that, I don't know. Or you could actually, you know what, instead of multiplying, you could just say replacing 1 with sine alpha over sine alpha, and that would actually probably be a little bit more clear. Let's do that. Replace 1 with sine alpha over sine alpha. Okay, that's probably better. That's essentially what we're doing. Then I'm going to combine my fractions. So I'm going to get the two fractions on top together by adding the numerators. That'd be cosine alpha plus the sine of alpha all over the common denominator of sine. So that's the top fraction, right? Those two combine. Then I have a big fraction bar. Now the bottom two fractions are a subtraction with the sign on the bottom, so it's cosine alpha minus sine alpha all over the sine of alpha. Okay, And so that's just combining fractions with the common denominator. Okay, combining fractions with LCD, okay? Then, when you're dealing with a complex fraction, we often think about multiplying by the reciprocal of the second fraction. So I've called this copy dot flip in the past. I need to get rid of some of my stuff over here because we're going to run out of room quickly. So maybe this becomes the sine. Nope, not the sine. This might become the cosine. Maybe I have room on the bottom. Let me go one more row on the bottom. Let's do cosine alpha plus sine alpha all over the sine. Then I'm going to multiply by the reciprocal of the denominator. Okay, so copy dot flip, multiply by the reciprocal. So we get sine alpha on top over cosine alpha minus sine alpha. All right. Now I notice here on that's using multiply by reciprocal. Okay, so now I notice that my sines cancel out, and I'm left simply with the cosine alpha plus sine alpha over cosine minus sine. Okay, so I'll write that out. Let's go over to the right here. Cosine alpha plus sine alpha over cosine alpha minus sine alpha. And that's just by canceling common factors. Okay, at this point, I pretty much have gotten a similar form as the original, so I don't know that I've made much progress here. And I'm not sure what else I can do from this point. There's no identities that we know of yet that have anything like this, cosine plus sine or cosine minus sine. There's nothing squared, so I can't use a Pythagorean identity. So I'm just going to leave it for a moment and come back to it. Maybe if we start tinkering with the right side, we'll get to that, or we'll get to something where I could make an adjustment. I might see something pop up. So let's do the other side, but I'm going to do that in red just to keep it separated here. Maybe I'll start with a similar idea, get everything in terms of sines and cosines. All right, I don't know. When you've done enough of these, you get a little bit of an intuition for it. The tangent is sine over cosine. So I'm going to call this 1 plus sine alpha over cosine alpha over 1 minus sine alpha over cosine alpha. Okay, so it turns the tangents into sine over cosine. That would be a quotient identity. Okay. We'll go through a similar step here, similar process. Let's get a common denominator with the cosine there. So let's call the 1 cosine alpha over cosine alpha plus sine alpha over cosine alpha. All over this 1 becomes cosine alpha over cosine alpha minus sine alpha over cosine alpha. Okay, so that's replacing 1 with cosine over cosine. Yeah. All right, that works. Now let's combine our fractions, right? Get those together, common denominator, so we get cosine alpha plus sine alpha all over the cosine of alpha. And divide that whole thing, big fraction bar, with cosine minus sine. So cosine alpha minus sine alpha all over the cosine of alpha. All right, so that's combining fractions with LCD. right? Getting some similar steps, some similarities. Just got sines and cosines and stuff in different places. Let's do the copy dot flip idea. Multiply by the reciprocal. Let's take this top, multiply by the reciprocal of the bottom. So let's take cosine alpha plus sine alpha over the cosine of alpha times, flip the bottom, you get the cosine of alpha on top now, with a cosine of alpha minus sine of alpha on the bottom. Good. We'll multiply by the reciprocal. Okay. Well, I noticed that my cosines cancel, right? One on top, one on the bottom. All right. Now I can only cancel common factors. I can't cancel terms off or anything like that. So just the factors of cosine cancel. So that leaves me with a cosine of alpha plus the sine of alpha over the cosine of alpha minus the sine of alpha. And that is by canceling common factors. And lo and behold, I have the same thing, right? They both simplify to the same expression. These two things are equal, which means the original two expressions are equal, right? I've got each of them to simplify down to this cosine plus sine over cosine minus sine, right? That one, this one worked its way down to there. So I was able to, the steps, or the three options that I erased over here, the third one said work with both sides and eventually get to a third equivalent expression, and that's what we did in this case. Now that may not always work. You know, sometimes you'll go one way, get to a dead end, go the other way, get to a dead end, and they're different. It doesn't mean they're not identical. The original aren't identical. It just means maybe you should go a different route, right? There's a lot of things you could do. I mentioned at the beginning, I could have turned the cotangent into 1 over the tangent and worked from there. Actually, that would have worked, and it would have gotten us directly to this side without going through this expression down here. But I just wanted to show you how you can do it a different way using, you know, working with both sides. So it would have actually gotten there quicker had I gone with the tangent instead of the sine or the cosine over the sine. And I kind of knew that already, but I just wanted to prove a point that this example can be done by simplifying the left, simplifying the right, and getting down to an equivalent expression on each side. Okay. Again, there's many different approaches you could take. Some of these, like, you know, here you could choose to go sine and cosine. You could choose to go with the tangent. There is some algebraic tricks that you could use that might work. You could multiply top and bottom by the conjugate of the denominator, do some weird stuff like that, which I'm not expecting you to really know how to do, but it could be done. And so there's many different approaches, but this I think was a nice one just to give you an example of where you can simplify both sides to a common expression in order to verify the identity.